Hey everybody, good to see you today. Did you know that we have the only company that makes large natural gas compressors in the world, in the United States? Practically. It's called Ariel Corporation. It's down on Blackjack Road. So, why is this so important? Well, Ariel is the only major company that makes devices that take gases, natural gas, which we get out of the ground, and turn it into a liquid. They make natural gas compressors, which, as you can see, are very complicated machines. But they're very complicated machines that make our town a lot of money and also allow us to heat our houses and run our industry. So let's take a look at where this actually lies in the natural gas system. So natural gas is a gas that's made, that is found underground, that is associated oftentimes with oil. But when you get it out of a well, you separate it into oil and water, because you aren't trying to get water that has oil mixed into it. That's not particularly useful. And natural gas. Natural gas goes into a plant, and you make all sorts of other things. You take all the other things out of it, you separate it, and then this is the important part for Ariel, a compressor station. So it's compressed and then sold, or it can be sent to your houses. Now, odorant is interesting. If you ever smell the smell of rotten eggs and you don't actually have any rotten eggs in your house, then you should probably get out of your house because you have a natural gas leak. CH4 is methane, natural gas, but they actually add in a sulfur compound that smells bad as an odorant, so that you realize the natural gas is there, because you can't smell CH4, you can't smell methane. And once it's compressed and transported, then it's turned back into gas that is actually a gas instead of a liquid, and then it goes to your house, or maybe to businesses or somebody else's house. Business, commercial things. So let's take a look at how we can study gases with our idea of moles that we've been developing. Now, there's a thing called the ideal gas law. We've taken a lot of look at gas laws before, looking at changes in gases. But this is actually just figuring out how many moles of the gas there are in a certain container. P is pressure. If you remember pressure, that can be measured in atmospheres or in kilopascals or in, PSI. But the one that we need to measure it in is atmospheres for the purposes of the ideal gas law. How many times the normal atmospheric pressure is it? For volume, for the ideal gas law, that needs to be in liters. Now, N is the number of particles. Number of particles is measured in moles. And then T is the temperature, which has to be in Kelvin. If you recall, Kelvin starts at 0 when there's 0 pressure. Celsius does not. So can't use Celsius in math problems because it's not proportional. Now this leaves this whole R thing. So R is a constant that makes this work. It's different for each set of units that you use. For the units that we're going to be using here, it's going to be 0.0821 liter atmospheres per mole Kelvin. Now I know that seems kind of strange, but what that really is just a number that makes the equation work and makes the units cancel out. Notice how it's in liters, atmospheres, moles, and Kelvin. So if you ever have something else like milliliters or kilopascals or grams or degrees Celsius, you have to convert to that before you can use this equation, because those are the units that this constant is in. So let's do a few of these problems together. There we go. Now remember, this is important for studying amounts of gases. How much methane will it take to heat something up a certain amount? Okay, it says what's the temperature of a 1 liter sample that has a pressure of 2.1 atmospheres and contains 0.083 moles of a gas? First thing we always do is write PV equals nRT. So you write PV equals nRT. Then we put in the numbers that we know. Well, we know the pressure is 2.1 atmospheres. We know the volume is 1.00 liters. Number of moles, 0.083 moles. We know R because R is always the same for us, 0.0821 liter atmospheres per mole Kelvin. Then we don't know T, so we're going to solve for the Kelvin temperature. But first, let's cancel some units. Hey, we've got atmospheres on this side of the equation and atmospheres on that side of the equation. Just like any other equation that we would have, we can cancel out the variables. So atmospheres cancel, liters cancel. Then we've got moles on the top and the bottom of the equation. So those cancel out. Okay, looks like the only thing we have left is Kelvin, which is good because that's what we're trying to find. So we take these things. I wouldn't normally write this out, but I'm writing out just so we're clear. And we divide both sides by all those numbers on the other side. I would just do this in my calculator. And we're going to get the temperature, which is 308 Kelvin. So how hot is that? Well, it's warm. It's nice. Well, how hot is that? How do we convert temperature to Celsius? Well, if you recall, Kelvin is equal to Celsius plus 273. So if I know the Kelvin, I can subtract 308 minus 273. That's 35 Celsius, which would be uncomfortably warm, but probably survivable for you. Okay, now I'll let you do this next one here. That's solving for pressure instead. So that's going to be in atmospheres. Notice that this is in Celsius, so you're going to need to convert that to Kelvin. Let's talk through some more of these problems. So this one, it's a two-stepper. Let's do one of those. It says a sample of nitrogen gas held in a container of volume 2.3 liters and a temperature of 32 Celsius exert a pressure of 4.7 atmospheres. So what it wants us to do is calculate the number of moles of gas present. So that is not, it's going to be a few conversions first. So let me write out PV equals nRT. And then we're going to have to convert some stuff before we can put those numbers in. So over here, I'm going to convert some numbers. PV equals nRT. So 32 degrees Celsius is what in Kelvin? So if you recall, Kelvin is equal to Celsius plus 273. So if I want to know the Kelvin, 32 degrees Celsius plus 273, my Kelvin temperature is going to be 289 Kelvin. Oh, by the way, back on number 1, I think I got the sig digs wrong. It's actually 310 Kelvin. Okay, so we converted to Kelvin, so I think we're ready to go. Number of moles of gas is going to be 4.7 atmospheres. Times 2.3. Oh, I just realized I did all this wrong. Hey, I looked at the wrong problem. that temperature is actually 305 Kelvin. Sorry about that. 4.7 atmospheres, 2.3 liters. We don't know what the number of gas particles is. 0.0821 liter atmospheres per mole Kelvin. And then 305 Kelvin was actually our temperature. So we divide, I'm not going to write it out this time, but for our number of moles, we get 0.43 moles is your number of particles. So that's the first half of the problem. We know how many particles are in there now. Now it says to determine the mass of nitrogen in the container. Well, we don't actually have to write out PV equals nRT again, because we know we have 0.43 moles of N2, 28.02 grams of N2 is 1 mole of N2, so it's going to be 12 grams of N2. So if I had a container that was 2.3 liters with a pressurized almost 5 times atmospheric pressure, I'd have 12 grams of nitrogen in it, which is actually why we transport natural gas as a liquid, often compressed, because that's not very much gas. So gases take up a lot of space to be able to transport very many particles. Alrighty, folks, I hope those examples help. Remember to convert always to liters, atmospheres, moles, and Kelvin, and then do the PV equals nRT. Thanks. I'll see you on the next video.